Well, welcome everybody. As he said, my name is Craig Benz, and you have stumbled into the life cycle of a widget, which is a talk about all the things, all the tricks at our disposal other than the build method. Now, I still remember when I was starting out in Flutter and I would read code from more advanced developers. Anytime I saw things like did change dependencies or add post-frame callback, I would always just think, what are those methods and how was I supposed to know about them? And like, are there other things like that? And anytime I needed to look something up and the answer was to put some weird code in did update widget, it just felt like someone was telling me to go in the bathroom, light a candle, stare in the mirror, say widgets 3 times, and then like my desired effect would appear. And very unsatisfying. So at the end of this talk, I'd like us all, I hope we're all going to be comfortable with the full rendering pass in the Flutter framework. We should all have a good concept of the life cycle of a widget. So that makes our first question, what exactly is a widget again? I keep hitting this thing. In Flutter, we like to say it's all widgets. And there's even a great podcast by that name. But how true is that statement? I mean, it can't all be widgets. There's also elements and build contexts and render objects and even things in our widget trees like box decoration and text style. They aren't widgets either. So it can't be true that it's all widgets. Is it even like mostly widgets? Well, if we get a little bit more flexible with the definition of the word widget, then the cute phrase can kind of more or less become true again. If we think of them as a discrete chunk of our UI with layered subcomponents, then we'll be pretty close. So Greg Spencer from the Flutter engineering team proposed the following definition for this kind of like conceptual widget idea. He said, it's a discrete block of an app's UI containing a static configuration, optionally some persistent state, and lastly, a render method. And that static configuration, that's the stateless and stateful widgets that we all write, and any of the framework widgets that they assemble. And the persistent state part, well, that starts to drift into the element tree and the build contexts that are passed back into our build methods. And as an aside, anytime we write a stateful widget, and then also write that backing state class, Flutter attaches that to the element. And those two things have a tight one-to-one relationship. For them, it really is until disposed do you part, because they never desync or separate in any way until they're being thrown in the garbage. And then lastly, the render method, of course, comes from the render object, which gets all of its information from the widget. So Greg's definition is a lot more interesting, especially for the purposes of this talk, because actual widgets have no lifecycle. If I just wanted to talk about the lifecycle of stateless and stateful widgets, then I'd already be off the stage, because they are dead objects that come off the Flutter framework's printing press, eyes closed, utterly lifeless, not responding to stimuli. They have no life cycle. They never change. So we're obviously not talking about that null case life cycle of those immutable configuration objects, but instead that kind of larger conceptual chunk of our UI. And so that means, of course, that the concept of a life cycle comes in at the persistent state layer. So we will mostly be talking about elements and state objects. But widgets was catchier for the talk title. So the first thing I want to go over is the shape of the various Flutter trees, the element, the widget element and render object trees, because they're not all identical, and the differences in their shapes can tell us things about how different code that we might write will impact the performance of our apps. So if we consider this pretty simple widget tree, I hope the white and the gray are different enough on this screen. But anyway, the white circle on the left is a stateless widget, then the gray circle is a stateful widget, and then the 3 blue circles are render object widgets, which you may or may not already be acquainted with. And a lot of Flutter developers know that every widget is backed by an element, and that element is the magical build context parameter that is passed into our build methods. So it's probably not too surprising to see that the element tree matches the widget tree's shape exactly. And we can see that state object there kind of stapled on to the element that our stateful widget was associated with. And as an aside, some Flutter developers have recently noticed and been kind of talking about the fact that the state object has its own context attribute, but that another reference to the context, to the build context, is passed into the build method. And this naturally begs the question, are these different in any way? Like, is there a reason to prefer one over the other? And earlier I said that those two things have an eternal one-to-one relationship, the state object and the element. So no, they are identical. There's no reason to prefer one over the other. The build context is redundantly passed into the state object's build method to mirror the build method signature of the stateless widget. So back to those trees, Flutter is not just a tree or two, but a proper forest. And so behind the element tree is, of course, another tree, the render object tree. But what do we think about its shape? How closely do we think it is going to resemble the previous two? Well, the answer is that it is a pruned version of the previous two trees. And to answer the question of how and why that happens, we'll need to look at the control flow between all of these trees to make sure we're clear on who is bossing around whom. So if you open up framework.dart and look at the widget class, framework.dart, by the way, arguably the most important file in all of Flutter, you'll see this create element method. And that tells us that it's widgets that create elements. And this kind of stands to reason because as Flutter developers, we obviously primarily write widgets. So Flutter should be learning about our apps from the widgets that we write. So widgets come first, widgets create elements. And ultimately, there are three main flavors of widget. There is, of course, stateless widgets, stateful, and render object widgets, which also technically has two subtypes, single child and multi-child, but we're not going to worry about those too much. Now, the type of element that each flavor of widget returns from that create element method is super important. But interestingly, we almost never override that method, which suggests that there's a tight relationship between that flavor of widget and the type of element that it returns, and that relationship is not something we as Flutter developers have to rethink or worry about. So here is an abridged implementation of the stateless widget, and we can see that create element method just returns a stateless element. So stateless widget, stateless element. Great. And then flipping over that coin to look at the stateless element, we see that it accepts a widget in its constructor, and the build method just delegates right back to the widget's build method and passes itself in as the build context. And then continuing on to the second flavor of widget, the stateful widget, we again see that its create element method just returns a stateful element. So stateful widget, stateful element. And there is the create state method waiting to be implemented by us, or rather our IDE snippets, because we are not typing that anymore. And then flipping over that coin to look at the stateless element, we see a couple of interesting things going on in the constructor. So it calls that create state method, saves the attribute, and then saves itself as the element attribute on the state object. And state.context, by the way, is just an alias to state.element. So we can see here that the state object's context attribute is definitely the exact same thing as what is passed into the state class's build method at the bottom as the build context. And lastly, the render object widget. Now this one starts to look a little different because it has no build method. Instead, it starts to know how to do something with render objects. It can create and update them. And then, because we're completionists, the final element, the render object element. Also no build method, and it's got some other methods that are important, and we'll get to those later. So we've just learned about these three types of elements, stateless, stateful, and render object elements, and we talked about how the stateless and stateful flavors don't render anything. And if the stateless and stateful elements don't render anything, then by extension, neither do stateless or stateful widgets, which is pretty interesting because those are the classes that we primarily write. So you might be thinking, how could it be possible that all the widgets that we write don't render anything? Like, Craig, my app does draw stuff. And that's true. Your app probably does, unless you're making a very weird app. But think about the visual impact that a single empty container would have on your app's layout. There is no impact. In fact, that's what we put in a build method when you're not ready to think about what the widget will draw yet. And the reason that a single stateless widget has no visual impact on our apps is because it doesn't produce a render object. So it is not until Flutter hits a render object widget in our widget tree before anything will ultimately be drawn to the screen. So this means that all those widgets we write, the subclasses of stateless and stateful widget, they're really just like middle managers. They don't do any rendering work. They only talk about rendering work. So here are some examples of the stateless widget from the framework. And obviously many of these are very familiar, but I also want to point out that they're very kind of high level. These are kind of design language, combinatorial concepts. We've got the drawer, the navigation bar, the scroll bar, whatnot. These are pretty complicated widgets. Similarly, some stateful widget examples from the framework, very familiar, but also pretty complicated things. App bar, navigation rail, scaffold, the most complicated widget in all of Flutter, in my opinion, not trademarked. Not the official opinion of Google. But anyway, similar to stateless widgets. Now contrast that with these render object widgets, again from the framework. We know a lot of these, but these are lower level visual primitives. These deal with things like layout, sizing, space, color, shape. So we can start to see how there's going to be this distinction between render object widgets, which know how to draw stuff, and stateless and stateful widgets, which only know how to arrange render object widgets. So let's consider this pretty simple piece of code. It's a container. It's got a color and padding and a text widget as its child. And let's talk about the three trees that this will ultimately make behind the scenes. At the top of the widget tree is, of course, a container, white again, symbolizing a stateless widget. Now, because we passed a value into its color parameter, then its build method will inject a colored box widget. Blue again, specifying a render object widget. The same for padding, because we passed a value, its build method will inject a padding widget. And then it finally gets around to the text widget that we passed in as the child. And the text widget this whole time has been a stateless widget. It doesn't know how to render anything. Who would have thought? It's just been lazy. But its build method can compile a rich text widget, which is a render object widget. And we said earlier that the mere flavor of each of these widgets completely implies the element that is returned from create element. So there's no surprises down the element tree line. So the stateless widget container produces a stateless element. The two render object widgets produce render object elements, and so on it goes. Which brings us to the render object tree. Now we said that stateless widgets and elements don't contribute to the render object tree. So for the container, there's just nothing there. But then the colored boxes create render object method knows how to return us a render colored box class. Padding also has its own specific render object, and the text widget produces nothing, and the rich text widget knows how to create a render paragraph value. So we can see here how the render object tree ultimately does become a pruned version of the previous two trees, and that's because the stateless and stateful nodes in the previous two just simply do not make render objects. But there's another implication here as well, because rendering or like performance issues in our apps will almost certainly come from rendering issues. And stateless and stateful widgets are just simple Dart classes that Dart can operate on very quickly. So it becomes true that more widgets in your app, especially widgets that we would write, will just not slow things down. So if you're ever looking at a piece of code and you think, man, if I could just wrap up this little chunk of logic in a stateless widget, it'd be very reusable. And this chunk over here, if I made that in a stateful widget, I could hide all this noise. But gosh, there's so much going on in my app. Is it too much? Am I going to like clog things up with too many widgets? You won't. So add the organizational layers because they don't even contribute to the render object tree, which is where things could actually slow down. And then ultimately that idea of the conceptual widget that we were talking about earlier, for that you can basically just pick any part in your tree, probably a stateful or stateless widget will do, and think about it, all of its descendants, and then their backing elements and render objects. And that will be a discrete chunk of your UI that will have a lifecycle and that you can put to work for you. So let's get into it. As a warning, there is some pseudocode ahead. Occasionally I omit parameters from methods that I'm not talking about, or I pretend two methods are right next to each other, but Really, there's like 10 other functions between them. We're going to get an accurate but high level overview here. So the class that manages rendering phases is called scheduler binding. And if you import flutter/schedule.dart, then you can access it via scheduler binding.instance. And this is set up by widgets flutter binding.ensure initialized, by the way, that we put in the top of our main method sometimes. Now this class has a lot of other methods that foreshadow the rest of this talk, but this class only actually manages the different phases. The rendering phases themselves live on an enum called scheduler phase that's found in the same file. And it has 5 values that, when visited in turn, constitute one full rendering phase in our apps. And the first phase is called idle. And this is kind of like the downtime between frames phase. So if you remember back in grade school, maybe you were taking a math test and the teacher would say, "Okay, everyone, when you're done, put down your pencils and sit quietly." It was like a huge point of pride to get done as fast as you could and peek at all the tests next to you and see how far ahead you'd gotten. Well, those kids could be said to be in the idle scheduler phase. But all kidding aside, this is where Flutter hangs out when it's kind of waiting for something interesting to happen. I often get this inaccurate idea in my head that as soon as Flutter finishes one frame, it just sprints right into the next frame. But that is not correct. Whenever Flutter finishes a frame, it's just like the rest of us, and it wants to do nothing until someone makes it do something, which in practice is because we either call setState or there's an active animation controller that's ticking. And the idle phase is also very important because it's the only phase where futures and streams are allowed to resolve. So if you think about it, in Dart, asynchronous code is never allowed to interrupt synchronous code. So if you say future.delayed, pass it 1 second, or tell it 1 second for its duration, it cannot magically guarantee that it will always be able to run that callback in exactly 1 second. Because if in exactly 1 second, Flutter is busy building widgets, then the future will have to wait until that frame ends, and Flutter makes its way all the way back to the next idle phase. And we can kind of glimpse into the idle phase and prove to ourselves that it exists by adding this code to the initState method of one of our widgets. And this will print schedulerphase.idle, despite the fact that initState does not run in the idle phase. It runs in the 4th phase, which we haven't gotten to yet. But the future just simply cannot resolve until the next idle phase. Now, the second phase is called Transient Callbacks, and this one is a pretty fun phase, I think, because this is when vsync events happen and when active animation controllers are allowed to tick and call their listener callbacks. And ultimately, the goal of animation controllers is generally to call setState, but it doesn't have to be. For example, we could again prove to ourselves that the transient callbacks phase exists by putting an animation controller like this in one of our widgets. And this animation controller would spend 1 second just spamming scheduler phase.transient callbacks as fast as it could, which is really high value. Also worth noting, anytime Flutter leaves the idle phase for any reason, which this animation controller would do for 1 minute or 1 second, Flutter will always go through all of these phases. It doesn't try to get cute and figure out if it could short circuit. Is nothing actually changing? It's just going to do everything. So less time in the idle phase for Flutter. Now, let's say you do call setState in your animation controller. With all this talk of different rendering phases and whatnot, you might be looking at this and thinking, wait a minute, why do we actually pass a closure to setState? Is this so it can pool them up and call them later or something? And that answer is no. Anything that we pass to setState is called synchronously and immediately. The reason that we pass a closure to setState is that in the early days of Flutter, UX researchers found that developers were forgetting to call the magical please render method. And folks were just setting values like this and then being like, why isn't my app changing? So wrapping all of that in setState and internally to setState, it calls the please render method, kind of just fixed all of that. So this is a great time, by the way, to look under the hood of setState. So here are its abridged internals. And as I promised earlier, the function that is passed in is called immediately. And if you've ever wondered how Flutter knows if you cheated and tried to await a future in that method, well, this is how. Because even a function that returns void, if if it's an asynchronous function, then it technically returns a future of a type void. And that's a thing that Flutter can just look at and then bark at you about. This also all happens in an assert, which means that the Dart compiler is going to remove all this gobbledygook from any production build of your app. So this is why if you try to profile your app in debug mode, you run the risk of just getting false positives for dropped frames and jank, because none of this code in the assert will even run in the production build of your app. And then lastly, at the bottom, we see that please render method that ultimately kicks off the next frame, and we'll revisit this method in a little bit. So the third phase is called mid-frame microtasks. And admittedly, this phase is a bit more esoteric. Now, sometimes in Dart, you'll see this schedule microtask function. And the first time I saw that, I thought, cool, what's a microtask? And luckily, that one is actually pretty simple. So anytime a future resolves, its callback kind of gets in the back of the line and waits to run after any other future's callbacks that are currently waiting in line. But microtasks are slightly different in that they just cut in line, so they get in the front. So the Dart runtime, before it executes any future callback, first tries to exhaust the microtask queue. So in this phase, Flutter just looks and says, have you scheduled any microtasks? And if you have, it runs them. Now, these methods can also be asynchronous. So you could write this, which prints the current scheduler phase, awaits future.delayed, and then prints the scheduler phase again. And if you run this, it will print scheduler phase.midframe microtasks, and then it will print scheduler phase.idle, because that future can't resolve until the next idle phase, even though we only wanted it to wait 0 milliseconds. It still just has to kind of hold its horses until the next idle phase. Okay, now the fourth phase is where things start to get a little bit more familiar, though its name kind of obscures its prominence a little bit. The fourth phase is called Persistent Callbacks. And for me, learning the name of this phase was kind of like finding out that the species name for dog is Canis lupus familiaris. It's like, yeah, I know what a dog is, but no, I hadn't heard that name before. So that's kind of like this phase for a lot of Flutter developers. Now, unlike transient callbacks, which deals with fickle things like animation controllers, which come and go, persisting callbacks is where Flutter calls its ride or die callbacks that persist for the entire run of the application. And Flutter has its own of those, like, rendering everything, but we can also register our own. So let's say you wanted to count every frame that your app emits. You could do this. And admittedly, it's a bit academic, but maybe if you have some flickering in your app, then logging a global frame ID variable might help you debug. But enough is enough. This is where Flutter gets to the good stuff. So we said earlier that elements and their state objects have life cycles, and we are going to start with elements. So for elements, their lifecycle is captured in this enum that also lives in framework.dart. And the initial state is the time between when the element is instantiated and when it's inserted into the tree. The active state is where the element spends most of its life while it's doing Flutter things. The inactive state is a brief state where Flutter kind of puts elements that it thinks it might be done with. And then at the end of every frame, any elements still hanging out in the inactive state get kind of rounded up and further demoted to defunct, and that's when dispose is called. So this pseudocode shows some of the lifecycle tracking stuff inside the instantiation of a new stateful element. So we see in its constructor, that same setup that we were looking at earlier, widget.createState is called. We see the initial state is actually initial in the middle. And then ultimately the mount method is called once this element is inserted into the tree. And we see a familiar face here, state.initState. That's where this is called. And then also the state is finally upgraded to active. And also the real mount method does tons more than this. It actually inserts this element into the tree and does a ton of bookkeeping and whatnot. But these are the bits that we care about. Fast forward to the end of this element's lifecycle, unmount will ultimately be called. And we see here that the state and element lose their pointers to each other. Dispose is called, and the final demotion to defunct happens. As an aside, in a recent Decoding Flutter, we talked about how the way to check whether or not a state's build context is still valid is to interrogate the state.mounted property. And I remember when I first learned about the state.mounted property and that it answered such an important question, I thought, that does not really seem formal enough to answer something so critical. I think I don't believe you. But it makes more sense knowing that state.mounted just checks whether or not the element pointer is still intact. And we just saw how when the stateful element is removed from the tree, those pointers get ripped apart. So state.mounted is the correct way to check whether or not your build context is still valid. And that is ultimately the lifecycle of an element, which brings us to the lifecycle of a state object. Now, state objects are way more interesting. Like elements, their lifecycle is also tracked in an enum, but unlike elements, we actually write our own state objects all the time. So we're way more likely to put custom logic in their milestone methods. So for that reason, I actually don't really like to look at the enum for the state object, but instead just look at the methods. And the enum is private anyway, so you can't even access it. So the following is a kind of lifecycle of a state object. And the two white circles represent possible entry points that the framework may use. That'll be the first method that it calls on a given state object within a given frame. So like init state obviously would be the first method called if it's its first frame. And then did change dependencies, did update widget, and build. They're kind of all in one circle because they happen sequentially in the same code. And we're going to look at that in a second. We'll also talk about them, except the build method. That was what I promised in the beginning. We're not going to talk about the build method. So first we have to actually make it to that lifecycle diagram though. So I want to discuss the code that runs at the beginning of a new frame in all of our apps. So either because our app is starting or because someone called setState, the platform dispatcher is ultimately asked to schedule a frame. And this is a handshake between the Flutter framework and the engine itself. And the platform dispatcher class comes out of Dart UI, we see, so it's quite low level. Ultimately, that calls draw frame on widgets binding.instance, and that's more machinery that's set up by widgets flutter binding.ensure initialized, which we again put in our main methods a lot. And then that ultimately calls buildowner.buildScope, and it passes in an element. So here we have a few new characters to get to know. First up is the build owner. What is that? Well, it's an instance of the build owner class, which is also defined in framework.dart. And the doc string for that says, amongst other things, manager class for the widgets framework, which is like, okay, sounds important. And this ultimately just juggles everything about widgets and elements in Flutter. So let's say, by the way, you can supply your own build owner. And anyone who wants to use the Flutter engine and embedder, but like doesn't like widgets for some reason, they would begin that task by supplying their own build owner. In practice, few people do this. So that moves us on to build scope. And when I saw this method for the first time, it was pretty unclear to me, like, what do you mean scope? What is the scope that we're building? Well, it takes in an element, and this method rebuilds everything below that element. So that is the scope. And at the start of each frame, the element that's passed in will be just the root of the entire application. But later on, if we have any layout builders in your widget tree, then it will be the layout builders element that is passed in. And we'll actually talk about that a little bit later too. Okay, so this build scope method, what on earth does it do? Well, it's pretty simple. I mean, there's a ton of other checks and bookkeeping and whatnot, make sure you're not rebuilding something out of scope, but essentially it just has a list of dirty elements and it rebuilds them all, and then it marks them each as clean. And that means that this rebuild method is obviously quite important. But before we dive into the rebuild method, I want to think about the special case that is the very first frame. Because in the first frame, there's nothing in your widget tree yet. Later on, Flutter is going to be doing all kinds of comparing of old elements and new widgets and seeing who's compatible with whom. But on that first frame, just a single kind of special method ends up getting called all the way down the tree. And that method is called inflate widget. And again, lots of checks that we're not going to worry about. It essentially calls that create element method that we were looking at earlier. That's finally getting invoked. And then the element that is returned is mounted onto the parent. And that ultimately is what builds the element tree. And then if we are in a stateful element, then that mount method calls in its state. And calling in its state means we finally arrived at the lifecycle of a state object. Now, everybody here knows init state. It's pretty popular. So Flutter continues on its way. It completes the rendering pass to wrap up the first frame, obviously. But that rest of the rendering pass is way more interesting after the first frame. Because that first frame, it's just inflate widget all the way down. I know you thought it was turtles. But we're going to now think about the rest of the rendering pass from the perspective of subsequent frames. So Flutter has finished up the first frame, and it's responsibly enjoying a drink at the bar, sitting in the idle phase. And then somebody calls setState. And whenever Flutter runs setState, that state object adds its element to a list of dirtied elements. And which list of dirtied elements? The one that was at the top of build scope that gets rebuilt every new frame. And remember, at the bottom of setState, there was that please render method. Well, that is where the element adds itself to the list. And then another side effect of this function being run is that it eventually makes its way to schedule frame, which is an idempotent method, which just means you can call it lots of times and it only does its effect once. And every time schedule frame is called, Flutter basically says, okay, fine, when I finish this frame, I'll do another frame. And that makes its way to the bottom of this same slide that we saw earlier. Build scope is finally called again. We're back in build scope, but we're ready to think about this from the perspective of a subsequent frame. And so now we can finally look at this rebuild method. Now, rebuild is kind of anticlimactic. It basically just does a bunch of checks and ultimately delegates to perform rebuild. And perform rebuild is finally pretty juicy. So the first thing that perform rebuild does, if we are in a stateful element and it's either new or some dependencies changed, is it calls did change dependencies. And this concept of a change dependency in Flutter means that an inherited widget that our widget has talked to changed. So if you ever write media query.ofContext in your app, and that line is executed, then your widget's element has been added to a special list, and then whenever the media query changes, your element will get rebuilt. And this happens right before the build method. So you can safely cache values in did change dependencies and then use them in the build method. So here's an example of that. We've got did change dependencies at the top, and we see that a size variable is saved off some expensive calculations from the media query. Right, the arrow. Good job. And then the size value is safely used in the build method. And this puts us here in did changed, or in the flowchart. And then, as we just said, right after that, the build method is called. Everybody knows the build method. If your parents had to rebuild, then you have to rebuild. And that puts us here in the flowchart. And then at the bottom of perform rebuild, this other method, update child, is ultimately called. And in update child, the juiciness continues. So update child has one of my favorite doc strings in the entire Flutter framework. It boasts the following claim. This method is the core of the widget system. It's like, all right, mad respect. So the first thing that this method does is check whether or not the element in question it should be deactivated. Maybe we've been scrolled past, maybe your widget got skipped in the last build method, whatever. If either of those things are happening, then the framework calls deactivate, and that puts us here in the lifecycle. And then if you finish the frame still in the inactive state, then you ultimately get disposed. Now, if you're not being deactivated, then the next thing this method checks is whether or not you should be reactivated, normally due to some global key shenanigans. And if that happens, then this method calls activate, and that brings us here to the lifecycle of our state object. But if you're not being deactivated and you're not being reactivated, then the next thing this method checks is whether or not you are a new widget. And in that case, it calls inflate widget. This is the code path that hits the whole way down on the first frame. So inflate widget gets called everywhere for the first frame, but then just for new widgets on subsequent frames. And of course, we've already seen inflate widget. And if none of those are happening, you're not being deactivated, you're not being reactivated, you're not a new widget, then this method is in the final scenario where an old element is being acquainted with a new widget. These poor elements, they just like sit there and speed date widgets, and then at a moment's notice, the framework will be like, LOL, here's your new widget, have fun getting to know them. And you know, the element has no say in the matter. But this all happens in the update method. And that method looks like this. And the first thing the update method does, if this is a stateful widget, is call did update widget, and it passes in the old widget. So that puts us here, by the way. Now, to better understand did update widget, I want us to think about this code real quick. We've got a gesture detector whose on tap toggles some state, and then a colored box, which is ultimately going to move from green to blue. So behind the scenes, that makes, I hope that looks green on the screen. It does not look green for me. It was supposed to be a green colored box circle. Anyway, we've got this tree here, and that render object element has been already acquainted with the green colored box. But then onTap is called, and the green colored box just kind of has to float away. They told me you couldn't animate things in Google Slides, and I said, that's because you have standards. So the green colored box floats away because these are immutable configuration objects and they can never change. And then a brand new widget is created instead, a blue colored box, and it just kind of slides in very elegantly. And when all of this happens, the framework calls this did update widget method, and it passes in the old widget, which always just kind of seems hard to keep track of to me, but maybe this helps a little bit. The green colored box is ultimately passed into the method, and the state object's widget property is already an updated pointer to the new widget. So a common thing here is to just check, did anything change that I care about? And maybe you start an animation controller to move you from the old value to the new. So imagine animated container like didn't exist and you were the first person to think about it. You could begin to implement it in this way. So then we're back in that update method, and after it calls did update widget, it calls rebuild, and that starts to work its way down the tree. And then we're back in the build method, but talking about our descendants. So this continues all the way until all the dirty elements have been rebuilt, but nothing has been rendered yet. Once all of the widgets and elements have been rebuilt and resynced, then Flutter finally moves on to layout, painting, and semantics. Except it's not strictly true that every single widget and element is rebuilt before layout, because remember the layout builder, whose entire purpose is to provide the available constraints at runtime? Well, the layout builder would have a super hard time doing its job if it had to run that builder before any layout had happened. So whenever Flutter encounters a layout builder in your widget tree, it pauses, switches over to the render object tree, waits for that to catch up to the spot, and then it takes that layout information, flips back over to the widget tree, and builds any descendants, and then resumes laying out. Okay, now upon hearing that, you might be thinking, I've heard that Flutter's layout algorithm is single pass. Does this violate that? And that answer is not on this slide. That answer is no. Flutter still only makes one pass down the tree for each frame. It's just willing to bounce back and forth between the widgets and elements half and the render object half. Okay, now we get to go to the next slide, which is the final phase, post-frame callbacks. And the signature to do something with post-frame callbacks looks like this. And it's a hook to just schedule some code to run at the end of the current frame. Now, by default, doing this will not actually schedule another frame. So you can just kind of run some cheap code here. But of course, if you call set state in this, then you will schedule another frame after the current one. And you can schedule a post-frame callback from anywhere, in a build method, in an init state. There's no limitations. But just because you can doesn't mean you should. So the first question is, why would you want to do this? Well, we just talked about how Flutter's rendering loop is single pass. And in practice, what that means is that any widget and element can only dirty their descendants. But that creates a bit of an issue if something going on in your current widget, say, changes the state of the overlay, which is definitely going to be higher in the widget tree than wherever you are. So that makes add post frame callback it makes changing the overlay a pretty common use case for add post frame callback. But that's not the only option. Another thing would be sometimes laying out one child and having their size depend on a sibling widget. Normally, the only way you could do that would be to write your own render object, which juggles the two and sizes them appropriately. But add post frame callback allows you to wait until the current frame is done, and you can always get the size of something that's already been rendered. And so then in the next frame, you can grab the size of the sibling and size the first thing. But there's a callback or a drawback, because this is a post frame callback. So one frame will have already been flushed to the screen, and your app will be forced to render that naive layout for at least one frame before it can get its hands on those juicy sizing details. And then we have pixels. That wraps up how Flutter makes a frame. It took me 42 minutes and 27 seconds to talk about it, but Flutter does it in just a few milliseconds. So thanks, everybody. There are some focus groups. The ones today, I think, are mostly full. But if you consider yourself a package developer, a desktop developer, or an iOS developer, then feel free to schedule a time. Some folks from the Flutter UX team are here, and they want to hear about your experiences. So we did it.
You can clap.